Hello guys, welcome back. Good to see you here. So today I want to do just Gaussian integral. Why not? Um, those of you who don't know, let's get into this without any yapping. It is my habit to just keep yapping. My friends complain all the time. Let's see. So we have an integral across the entire x-axis of this function here, e to the negative x squared dx. For your viewing pleasure, this is what the function looks like. It's actually a bell curve. It's symmetric and has an asymptote on the x-axis where the curve just goes like this. And it's basically like the normal distribution function where the mean is equal to 0 and the standard deviation is, I think, 1 over root 2. Don't ask me why, but yeah, that's... And it does link to standard deviation and normal distribution in a way, because in the formula for normal distribution, you're going to see a certain... What is what is this? You're going to see you're going to see a certain constant that really creeps you out. Essentially, it's like this. So the normal distribution function is like this. And what on earth is this root pi doing here, right? And my job today is to show you what on earth it actually is doing. Like, I know what the dog is doing. Let's see what's going to happen. So let's start off with the integral across the entire domain of e to the negative x squared dx. This is a non-elementary integral, so there is absolutely no traditional closed form way to express this function's antiderivative. It has to be written as the error function, whatever it is. But given that we have a definite integral with limits, we can actually do a little bit of manipulation. So our journey starts off by writing this as this integral here. We haven't changed anything, we've just changed the name of the letter of the variable that we're using. And just a quick note, this is something for you guys. These are not actually variables, they are dummy variables. Essentially, it means that, yes, they are variables, but once we find the integral to this, we're just going to be replacing x with infinities anyway, right? So it's not a variable, it's just going to be replaced with a constant. So therefore, it's like a dummy variable. It's like a puppet state, essentially. All right, so this means that the integral can be rewritten as like this. So we have the integral in terms of x multiplied by the integral, same thing, just in terms of y, but with a square root around it, a big, massive, juicy square root like this, right? This is the exact same thing, because we're just multiplying an integral by itself and square rooting it to get back to the integral. We haven't changed anything. All we've done is this weird thing. And now we are legally allowed, actually, to combine these two integrals into one big double integral because of the fact that these functions, well, first up, they're continuous. Secondly, they converge, right? So this can be rewritten as an integral going from negative infinity to infinity of a second integral with the same domain, I guess, of e to the negative x squared times e to the negative y squared times dy and times by dx, right? So essentially, the idea with a single integral is that you have like a function, right? And you're trying to find the area underneath it. However, double integrals, they can be sort of expressed as sort of a 3D shape of some sort, and you're trying to find the volume inside the shape, right? Across 3 axes. It's really, really weird, but we're just going to stick with it for now. And another way to think about a double integral is that we have a single integral in here, and once we've found the integral, the answer to that integral, we can integrate it again with respect to the second dummy variable, right? Anyway, let me just combine the exponential term into just the two terms into just one term, right? And it should be written as e to the negative bracket x squared plus y squared, like this, okay? Just the same thing, I've just combined the exponents into one and I factorized the negative outside, outside the bracket. Okay, Now we're going to use the traditional polar coordinate integration method to compute this. It is a little confusing, but essentially the idea behind this is you have a Cartesian plane, right? Y-axis, x-axis. X represents the distance from a point over here to the origin, right? Going horizontally, and the y expresses the vertical distance, or should I say displacement, because we can also have negative values. So this point here is represented by, let's call it xy. However, polar coordinates, they work slightly differently. So I'm going to denote that in blue. Polar coordinates can be written in terms of r and theta, where r is the distance from the origin to the point, like directly. We're not splitting the distance into components, into vertical and horizontal components, x and y. We're just calling it one single magnitude diagonally from the origin straight to the point. And theta is just the angle made between the r line and the sort of x-axis, right? This angle over here, right? That's what theta is meant to be. And we have a right angled triangle. I'm just going to redraw it here to make it clear for you. We have r and we have theta. We have x and we have y. If we use the trigonometrical, that's not even a word. If we use the trigonometric properties of this triangle, this right angled triangle, firstly we can derive that x squared plus y squared equals r squared. This is actually the formula for a not a unit circle, for a general like circle with a center at 0, 0, if you're interested in that. And secondly, we can get that the opposite side, the side opposite to the angle, which is y, over the hypotenuse equals to sine of theta. We also get that the adjacent side, which is x, adjacent side to the angle, divided by the hypotenuse equals cosine theta, where the hypotenuse is just the side opposite to the right angle. From this, we can say that y is equal to r sine theta and x equals to r cosine theta. Okay, so now that we have everything that we need, not quite everything, but we can transform this integral into a double integral. This double integral, sorry, it's already a double integral in terms of x and y. We're just going to turn it into r and theta. So we're going to worry about the integration limits later on, because that's where it gets a little confusing. I'll try and make it simple. Let's just focus on the integrand, the expression inside the integral for a second. So we have e to the negative x squared plus y squared. From earlier, what we derived is that x squared plus y squared just is r squared, right? So I'm going to write that as r squared. And now dy dx. This can be written as dr d theta multiplied by a certain factor called the Jacobian with respect to r theta. The Jacobian is basically, how do I explain it? So you have the Cartesian coordinate system, right? The rectangle coordinate system, and then with the y and the x-axis, right? And then you have r and theta with some sort of polar coordinate thingy, which can be written like, drawn something like this, right? Whatever the drawing is. Or in terms of a circle, right? Essentially, no, I don't even need to draw that. We're converting a rectangle into a sort of curved piece. So this piece here is being transformed into this piece over here. And the issue with doing this is that each individual rectangle piece being mapped onto each individual curved piece, right? There's going to be a sort of warping or distortion factor. Is my camera even is working? I should have checked that a long time ago. But we have a warping, distorting factor that we have to account for every single piece. And it turns out if you average that, you get something called the Jacobian, right? And yes, there is linear algebra involved here. We're going to have to use matrices. It's simple. It's just simple matrices. It's the determinant of a square 2x2 matrix. Pretty simple. So what is that matrix going to be then? So the Jacobian with the variables r and theta can be written as the absolute value. I'm just going to say like this, of the determinant of the following 2x2 matrix. Okay, that matrix goes like this. I think it's like partial derivative of y with respect to r, and of y with respect to theta, and of x with respect to r, and of x with respect to theta, right? Once again, recap partial derivatives. That's like you have an expression with more than two variables. For example, from earlier, we had y equals r sine theta. Essentially, the partial derivative of y with respect to r means that we treat anything else apart from y and r as a constant. Therefore, theta is a constant, and we just differentiate this thing with respect to r, we just get cosine, right? If we do the same thing with theta, dy over d theta, partial y over partial theta, is equal to negative r sine theta, sorry, because the sine theta, wait a minute, I got it the wrong way around. It's r cosine theta, because the sine theta differentiates to cosine theta, and the r is treated as a constant because of the partial derivative with respect to theta, right? We can do the exact same thing with x, partial x over partial r. Before I do that, actually, I'm going to write that x equals r cosine theta. Partial x over partial r is equal to cosine theta, and partial x over partial theta is equal to negative r sine theta, because the cosine differentiates to negative sine and the r is treated as a constant, right? And so the determinant of a matrix is basically the difference of the products of the diagonals, right? So it's going to be, the determinant is just partial y over partial r, partial x over partial theta, minus partial y over partial theta, partial x over partial r, with a modulus going sort of surrounding everything, right? Anyway, partial y over partial r, as we said, from here was cosine of theta, right? So I'm just going to highlight that in yellow like this, cosine theta, right? Partial x over partial theta, which I'll just do in green, is this thing here, which is negative r sine theta, like this, okay? Then we have the minus sign in the middle, and partial y over partial theta, which I'll just do in blue, or cyan. I think it's a light blue anyway. Partial y over partial theta is r cosine theta, like this. And finally, we have, oh, I'm running out of highlighter colors. Let me use orange. Partial x by partial r gives us cosine theta, right? I'll just do that like this, and we have the absolute value going around it. So if I am to make this simpler, we get negative r. Wait a minute, have I made a mistake? Wait. Yes, I have made a mistake. I'm so sorry for this. Essentially, my mistake here was differentiating both the r and the theta. I'm so sorry for that. I was just meant to differentiate the r, and you just get sine theta. Okay, that's my mistake. I should probably, you guys, I owe you guys a few money, pounds, whatever. But pretend I didn't do that. Just let it slide. Okay, forgive me, guys. I don't want to lose subscribers, right? I don't want to get cancelled for doing a differentiation wrong. Anyway, we have negative r times the sine theta times sine theta, and negative r and cosine theta times cosine theta. If we are to factor out the negative r, we get sine squared plus cosine squared theta, which, as you know, this is just the Pythagorean trig square identity, which is just 1, right? So we get the absolute value of negative r, which is just r, right? And that's what the Jacobian collapses to. It just collapses to a single letter, right? Which is just r, right? So we have the double integral of e to the negative r squared dr d theta with just the r. I'll just put it in the front. Now we can worry about the integration limits, right? So I'm just going to draw a Cartesian plane again with a unit circle, or just not a unit circle, just a circle in general. Essentially, our y and our x values go from negative to positive infinities, right? And if you think about the circle, as x and y go to positive infinity, we get that r also goes to positive infinity, right? As x and y go to infinity. as x and y go to negative infinity, we get r going to positive infinity. Anyway, the reason for this is because r is just the magnitude. It's a distance from the origin to the point, right? So r is going to be a positive number, which means that the minimum value of r is 0, which means that r is on the interval from 0 to infinity, right? I'm just going to write it like this, 0 to infinity, okay? How about theta? Well, given that we have a circle here, theta can just take any of the angles, right? It just maps out an entire circle, which means that theta is between 0 and, you were going to say 360. We are adults now. We work in radians, 2 pi, 0 and 2 pi. So now let's do this like this. The r limits are 0 and infinity. The theta limits are 0 and 2 pi, right? Now we can actually compute this integral properly, because it's something that we can genuinely do. So let's work on this inner blue integral first. I'll do it over here. So the integral from 0 to infinity of r e to the negative r squared dr. Well, there's many ways to do this. I'm just going to take a u substitution. Let's let u equal to r squared, okay? And differentiate both sides implicitly. And we get this. Du equals 2r dr. And we get the integral of r times e to the negative r squared, which is e to the negative, that was r squared, which is u, times du over 2r. That's because du over 2r equals to dr. And the limits of integration, what are they? Well, as r goes to 0, u will just also go to 0, right? And as r goes to infinity, u also goes to infinity, okay? So, like this. Therefore, thankfully, these r's over here that were really causing trouble cancel out, and we just get the integral of e to the negative u du, which, if you integrate this, you get negative e to the negative u. Fun fact, this is also the derivative of e to the negative u, but that's just because of the way how exponential functions work. If you differentiate or integrate an exponential function, you end up with also an exponential function, just differing by some sort of factor. In this case, that factor is -1. So if we plug in the limits, 0 and infinity, of course I'm abusing notation. I should be using limits, limit as some, like this, right? Limit as some letter goes to infinity of that some letter, right? But essentially that becomes negative, what is it? Limit as a goes to infinity of negative e to the negative a minus negative e to the negative 0, right? And if you put infinity into this, essentially e to the negative a can be written as 1 over e to the a. And if you put infinity into that, you just get 1 over astronomically large number, which goes to 0, right? As a goes to infinity. So this first part, this limit is equal to 0. Then we have minus, well, this e to the negative 0 is just 1, so we have -1, which gives us 1. So the inner integral is 1, right? This means that we have the square root of the integral from 0 to 2 pi of the blue thing happened to be 1, and then finally we have a d theta just chilling on the outside, right? If you integrate that with respect to theta, 1 just becomes theta. Plug in the limits 0 and 2 pi, and you basically get square root. Wait a minute. Wait. I've seen my mistake. Mistake number 2. I've forgotten about this 2. So that 2 would have basically stalked us all the way here, which means that our answer wouldn't be 1, it would be a half, right? I'm so sorry about that. Let me just, it's been a long day today. Half, right? So half theta, which means that if you put the limits in, you get 2 pi minus 0 with the square root. That's just 2 pi times a half, which is pi. And the square root remains. And quick reminder, this just equals to the Gaussian integral. I've now shown you why the Gaussian integral is root pi. Okay, before I end this video, I also want to talk about the normal distribution a little bit. The function given over here, right? E to the negative half, whatever that is, and why the root pi is there. I'm actually going to show you via a substitution. So essentially the area, the entire area underneath a normal distribution function, for those of you who take A-level maths like statistics and just statistics in general, you're going to know that the area underneath the normal distribution curve like this, the total area is just going to be 1, no matter what values of mean and standard deviation that you use. I'm going to show you why it's always going to be 1 using a substitution with an integral. So essentially, we have the integral. The entire area underneath the curve, I'll call it capital A, can be represented like this: e to the negative half x minus the mean over the standard deviation squared over root 2 pi times the standard deviation. So mu and sigma, right? Why those letters? Because I'm muing and I am a sigma, right? That's why we use those letters. It makes a lot of sense to me anyway. If you just quickly take a substitution, let z equal to x minus mu over sigma. This is a particularly famous substitution to use because this is called, statisticians call this the standard normal distribution, which is basically normal distribution, but where mu is 0 and sigma is 1. Okay, this is not quite the same as the Gaussian curve. This is because, you'll see. Anyway, let's just differentiate this with respect, just implicitly, sorry. We get dz equals 1 over sigma dx, and sigma dz equals to dx. So this integral can be written in terms of z, purely just z, right, under all these weird things. So you're going to see. The reason why the limits of integration don't change is because this sigma over here is always positive. It can't be 0 because you get something undefined. It's always positive. It's just the distance, how farly spread the data of a sample are from a given mean, and the distance, that's just a magnitude, isn't it? That's just a positive value. So x minus mu over sigma, the sigma is always positive. So z and x minus mu are just directly proportional to each other, and they have a positive sort of, I guess, proportion to each other, which means that the bounds of integration must not change. The rest of the integrand itself, is e to the negative half x minus mu over sigma squared is z squared. Okay, and then we have over root 2 pi times sigma. Finally, the dx is sigma dz, right? So sigma dz. And note that the sigmas cancel out, so there's no more sigma sort of in Ohio left over. We just have this integral over here, e to the negative half z squared dz, with a 1 over root 2 pi attached to the front as a constant multiple. Now, how do we get from this to a Gaussian integral, you may ask? I'm just going to take another substitution for ease of mind. Essentially, I want negative half z squared to equal to negative, let me pick another letter. Let's be exquisite and use gamma. Gamma squared. I want it to be negative gamma squared. This is, I know it looks like the Euler-Mascheroni constant, but trust me, it's gamma, right? This means that half z squared equals to gamma squared. If you square root both sides, you get that gamma equals 1 over root 2 z, right? Which allows us to differentiate both sides implicitly and multiply both sides by square root of 2 to get square root of 2 d gamma equals dz. Finally, this integral can be written as 1 over root 2 pi times the integral going from negative infinity to infinity. The reason why the limits of integration don't change is the same reason here. Gamma and z are just like directly proportional to each other with a positive factor of 1 over root 2. So the integrand then, e to the negative half z squared is e to the negative gamma squared, thanks to our substitution. And dz was just equal to root 2 d gamma. Okay, so this can therefore further be written into 1 over root 2 pi, that's just root 2 times root pi. And this root 2 over here can be brought to the outside of the integral, right? And then we have things left over. And fun fact, these root 2's they actually cancel, giving us the integral going from negative to positive infinity of the e to the negative gamma squared d gamma over root pi. And is this familiar? It is familiar, this integral over here. This integral is totally familiar because the integral from negative to positive infinity of e to the negative x squared dx is root pi. All we have is just gamma instead of x, and that doesn't change anything because they're dummy variables. They can just be replaced with each other. They're literal objects, right? They're like this piece of cloth right here. No one cares about them. They're dummy variables, right? Because they're just going to be replaced by the integration limits anyway. Therefore, they are just interchangeable with each other. This x and this z and this gamma and this whatever. So that's why the numerator of this expression is just root pi. The denominator is root pi. What happens when you divide them? You get 1, which from the start was just equal to the area underneath any normal distribution function, with any valid mu and sigma values, right? So I'm happy to say that this proves that the area underneath any normal distribution function is just 1, okay? Let me just... Are there any closing statements? What on earth is going on here? Are there any Yes, there are. So, despite the fact that my battery is just dying, it's at 10%. Please mention in the comments any video ideas that you may have. I have one coming up. It's about the integral of the reciprocal of the general quadratic. It's really interesting. I have another one. I wanted to do like an entire A-level maths paper on camera because I only have exactly 1 month left till the exam. It may be a good idea to do that, right? And if you have any other ideas, like let me know, because I'd be willing to consider them, right? With that being said, give me my likes and my subscribers going on here, and subscribers, please. I'd really appreciate it. Have a nice day. Enjoy what you're doing.